Sendhil, any chance we could get you to jump right away?
I will pick up on one of the pieces Marzieh alluded to. And what I want to do is I want to sort of tell a story here in 3 parts. And as Marzieh mentioned at the end, I'm fundamentally very, very optimistic about the role of healthcare, about the role of AI in healthcare. I'm saying that because this is going to sound like a very pessimistic talk. And the title is already pretty pessimistic. So let's start with 3 stories. The first story is very brief, and it's not even my own story. This is a story by Mukund Sundararajan, who's a researcher at Google, who has done a lot of work on sort of interpretability techniques. So this is from the early days, which is not too long ago, since this field is so fast moving, about 3 years ago, 4 years ago, I think at this point, of a Google team that had worked out an image pathology model, which would take X-rays and would detect pathologies in those chest X-rays. Now, 4 years ago, it was sort of, as you saw in Marzieh's chart, reaching human performance was not something that had been done very, very often or even at all. So this team was like ecstatic because with their pretty large set of X-rays, they had built an algorithm that out of sample could do as well as clinicians in detecting pathologies. In fact, it was doing better in a sense we can get to later, but it was doing as well. So it was really quite a big success. And just out of sheer curiosity, because they knew their colleague Mukund had been working on interpretability techniques, they said, hey, Mukund, can you help us we're just curious, how is the algorithm doing this activity? Explainability in a slightly different sense than Marzieh meant, and I'm going to end the talk on that, but you can see you built this model, you're like, hey, what is the algorithm doing? What is it seeing in the X-rays? So they went and they did these techniques which allow you to, on a given X-ray, sort of isolate and give heat maps of the areas where the algorithm is getting the most signal. So in this particular X-ray, it was over here. So they're like, oh, what's going on over there? Let's zoom in and adjust contrast, and you get this. What is that? So that's what the algorithm was picking up on. What is that? Well, what it is it's pen marks. Radiologists from the system who've been working with these X-rays would make physical pen marks on the X-rays when they noted something. Now, this is a major problem because this means this was not an algorithm that was detecting pathology. It was an algorithm that had detected pen marks, which is about as useless as you could get. If the goal were, we want to build an algorithm that would then do something the radiologist could do, building an algorithm that simply just found the traces of what the radiologist left behind is the worst possible outcome. No wonder it was doing well. It wasn't actually doing the thing it was supposed to. And one way to think about this is that the performance was very high. Our metrics for evaluation were well executed. It was out of sample, etc. But high performance didn't actually mean high performance. And to call it distribution shift, which is often what people allude to in these cases, like somehow you trained on one data set, but really it's a different data set that we're looking at, is kind of minimizes the problem. What's happening here is there was a feature of this data that led it to be buggy. There was a bug in the sense that we tend to mean bugs in code, but it was a bug in data. That is, in this data, pathology, X-rays with pathologies also happen to have pen marks. This problem that an algorithm that appears to be working, but is in fact infested by a bug, and a bug in data is an incredibly common problem, not just in healthcare, very broadly speaking, but it is particularly problematic in healthcare for reasons I'll talk about. So the analogy I want to form here for you is all of you is programmed at some point. And when you program, the bane of your existence is bugs in code. We recognize them and we fear them. And a bug in code is when we think the code is doing one thing, but it is actually doing something else. Well, ML systems have code as well, obviously, so you have to program these up. But the bugs in that code is very, very small lines of code at some level. The bugs there happen, but they're not the first order bugs. Where are the first order bugs? Well, ultimately, if you think of the final algorithm, not the one that's the trainer, but the trainer works and produces a predictor, that prediction algorithm, that's actually formed not just through the code, but the training data. In many ways, the training data can be thought of as the means by which you actually are coding the algorithm. When you take that analogy to its logical extreme, you'll say, oh, I see, that opens up another avenue for bugs. In this case, it is just as before, but it is that we think the data is one thing, but it is actually something else. The Google team thought the data was X-rays with labels for pathologies, but it wasn't quite that. It was X-rays, labels for pathologies, along with some pen marks. And that kind of misunderstanding of one's data is fundamentally problematic and creates many of the bugs we see. And I'll give a little aside here. It's worth noting that all of ML, not all, but almost all of ML suffers from this for the following reason. Typically, when scientists work with data until the last, before the last 20 years, it was constructed data. Surveys would be done, a lot of thought would go into who was surveyed, how they were surveyed, all parts of it were constructed. Bugs in data was known as survey methodology, and we knew what it all was, and we understood the problems in survey methodology. Take anybody who's working with a data set in AI right now and say to them, where did you get your data? Well, they would know where they would got it. Okay, how was the survey done? Oh, I don't think it was a survey, it came from a system. Modern data sets don't often have surveys, they are found data. So we are just guessing at some level what's in them, and that's the source of this problem. This data set was not a survey where we took a random sample of X-rays of patients and then had a survey method for having radiologists look at them. It was data that came from the health system, and hence the bug. So that's why I think bugs in data are pretty problematic in healthcare. Let me show you a project that I was involved in a little bit that had that I think had one such bug. So this is a program, as Marzi mentioned, there are already algorithms scaled in healthcare, and this was one such algorithm. So what did this algorithm deal with? It dealt with the fact that patients with a lot of chronic conditions, so you have somebody with diabetes and heart disease, patients with multiple chronic conditions are really where most of the spending in healthcare goes. As a result, people have developed programs to say, hey, if we can help those patients, we can save a lot of costs. Give them a dedicated nurse so that they know when to come in and when not to come in. So people have created these programs. They're called care coordination programs, hence the title of this slide. The question, of course, is these programs cost money. Who do we give them to? That's where these algorithms come in. These algorithms are used to target patients for such programs. They're already at scale, roughly 100 million patients. 100 million patients these algorithms are being applied to roughly 100 million patients. And what they do is they aim to say, based on your medical history, will you be a person who needs a lot of care in the next year? If so, we're going to give you a high score, and then you'll be more eligible for these programs. Okay, so what did we do? Well, as Marzia mentioned, there are a lot of racial inequities in the healthcare system. So here we have access to one sort of live, large-scale private sector algorithm with some consequences for who gets in the program. And we should look at whether the algorithm has a racial bias. So what kind of whites and blacks would be chosen for the program? So to assess that, what we're going to do is look at something in this literature they call calibration. So put simply, I'll just show it to you in the figure. On the x-axis, I've got the algorithm's risk score. On the y-axis, I have how sick the person actually turned out to be. So higher risk, sicker. That makes sense. The algorithm is doing its job as it should. Now, why are there two lines here? That's because the bottom line is for the white patients and the top line is for the black patients. You can see here at every predicted level of risk, the black person turned out to be much sicker. And I'll show you how much in a second. Blacks had 28% more chronic illnesses at this threshold where they would have been automatically enrolled. So, and this is true of many other health outcomes. So let's zoom in on that region. You see, this is the region at which you would be automatically enrolled. This gap, what it means is that a person to the left of this line, a black person over here, is being left out of the program, when a white person to the right of this line over here is getting in, who's far less sick. If we were to correct this inequity, as you can imagine, what you'd want to do is you'd want to add in the left out very sick black person, remove the less sick white person, and keep going until you have people at the margin of the same health. So you can get a sense of how discriminatory this algorithm was. If you simply simulated that process, you would more than double the number of Blacks enrolled into this program. So what you see here is a epic failure, which is you see that this program being applied to 100 million people already and continuing to be applied is actually seriously discriminating against Blacks. So what's happening? How did the algorithm go wrong? Well, one place you can get a sense of how the algorithm goes wrong is to understand where the algorithm is going right. I'm going to remake that exact same curve for you, but I'm going to make it this time risk score on the x-axis, but instead of sickness on the y-axis, I'm going to put healthcare costs on the y-axis. And now you see there's no gap at all. The algorithm was well calibrated for health costs. It was not well calibrated for health. What had happened was, I should say, the algorithm had been asked to predict care utilization. But of course, Blacks and whites don't have the same relationship between how sick they are and how much care they utilize. Whites have better access to healthcare. So as a result, Blacks utilize less healthcare. So accurate prediction of utilization means biased prediction of health. It's a very subtle error because how do you know if someone is sick? You know it if they utilize care. So as a result, the problem was in the label that was chosen to train this algorithm. The algorithm did the right job. The code worked. It optimized the objective it was given, but it wasn't the objective that we had. And the reason this utilization and health are so close and hard to see their difference is because we tend to use them synonymously as people. How do we know someone is sick? Because they're in the hospital, they utilized care. Of course, they're not the same thing because you can have high blood pressure but not show up. But that subtle distinction gets lost here, and then we have this huge problem. And so I wanted that to be the real example that's the equivalent of pen marks that had massive consequences. And I think the reason there are data bugs such as this are a fewfold. First, healthcare data is always repurposed data. This is something people have to keep in mind. There are a few carefully collected surveys like the Framingham study, but by and large, nearly every data set used to train an AI algorithm or an ML algorithm is data that was created for an entirely different purpose and therefore has totally different properties. For example, it was created for billing purposes, for workflow purposes, but yet now it's suddenly being used as a source of clinical truth. And you can see how a lot of bugs show up at that moment. Another reason that there's a problem is you have to remember, we rarely measure anything consistently. We do not have a system that sits there and says, I will take blood pressure for everybody at a certain cadence. We do measurements when we think there's a problem. For example, many sepsis predictors out there. Sepsis is a form of extreme infection. It is to infection what metastasis is to cancer. It's when the infection gets out of the box. It's a source of a lot of deaths, and there's a lot of people aiming to predict sepsis. They tend to take electronic health record data and they tend to predict sepsis, and they say, hey, we do a good job. When you look at many of those predictors, you tend to find that the most predictive variables are actually kind of weird. For example, you'll find that one variable that's highly predictive is, did the patient have a blood pressure measurement? Not what was their blood pressure value, but did they even have one? Why is that predictive? Because when a patient is thought to be getting really sick, you do a blood pressure test. So this is no longer a sepsis predictor. It's playing back to us what we already knew. Hey, I noticed you doing a blood pressure measurement. I'm guessing that means the patient's sick. The doctor is saying, yes, that's why I'm doing the blood pressure measurement. So you can see that the lack of consistent measurement creates a set of problems. Finally, the other reason that there's an issue here is we rarely have the right sample. There's a couple of versions of that. The first version of that is a paper that came out recently in JAMA. This was quite a nice paper. It just said, what is the geographic distribution of US cohorts to train these algorithms? Now, you'll notice that if you see this, you'll see Massachusetts and New York and California play a huge role here. Why are Massachusetts, New York? Well, you can imagine why those are the three places where we get all our data. We're not training these algorithms for healthcare. We're training them on the patients that show up in a few academic medical centers and are treated the way patients are in academic medical centers. Now, I think most of you who know anything about healthcare know that academic medical centers are like nothing like the rest of healthcare. Like nothing. I mean, it is a totally different world, both in disease distributions and care practices. So it's such a weird sample on which to train and draw inferences from a whole population. So that's one sense in which we don't have the right population, but we have another sense in which we have the wrong sample. We have data on the people who are diagnosed or are biopsied or showed up. This is easy to forget when you start with your sample, but you have to remember there is a huge sample selection problem in every one of these data sets, one that is almost always overlooked. In some contexts, we call this a selective labels problem when you only have the outcome for the people that you've looked at, but there's even a sample selection on the way in. I thought this was a very nice paper by Suresh and Gutag that you should have a look at. They try and talk through all the different biases through the pipeline. A lot of these biases that I'm describing are here, as well as a few others. So that's the reasons for the bugginess that I've laid out. I want to conclude on something that's a little different, but will change the note on which I hope you take away from this. So this is a paper we recently finished. I was a collaborator on. Emma Pearson was the lead author on this paper. And this paper deals with pain, specifically osteoarthritis or knee pain. For those who don't know, knee pain is an incredibly common occurrence. You probably don't know because you're young, but this is about 10% of men over 60 have knee osteoarthritis. And one of the interesting facts about knee pain, tragic facts about knee pain, is that the poor and Black patients and less educated patients suffer a lot more in pain. So if you give them a pain score, it's called the Coos pain score, and you just ask them, in how much pain are you? You'll find a big race gap, a huge race gap. I'll get to how big it is in a second, but quite a big race gap. Of course, there could be some reasons for this gap. One of them is, well, maybe there's something wrong with their knees. They have worse knee ailments, and that's why they're in worse pain. The other theory is that, look, the same physical ailment has different psychological effects when you have stress, life stress, or you have less access to pain medication, et cetera. So one theory is it's inside their knees. The other theory is it's outside their knees. So people have tested this. In our data, we test this. But what do? Easy. We find out how severe the knee ailment is, and then we condition on it. So we say, here's how bad the knee ailment is. There's something called a KL grade, which is what clinicians use to judge severity. And here's how much pain there is. For some perverse reason, pain scores go in the wrong direction. So the lower the score, more pain. I don't know who invented this score. Well, I do know who invented the score, but it is a perversion. And what you see here is you see that at every level of severity, Blacks experience more pain. So conditioning on severity does nothing. This is the received wisdom in the literature that, oh, I see. Even holding constant severity, there's something about race that magnifies your experience of pain, socioeconomic status, access to care, whatever it is. So you can see the gap barely changes in any of these cases. Okay, what I want to ask is, does this settle the matter? After all, medical knowledge is mostly in flux. It's still why we're still doing the science. We can't explain pain very well. This KL grade is just a human made up thing. What if we flipped the entire script and said, maybe there's something in the knees that clinicians don't know about? What would we do? Maybe there are overlooked features, and that's why people are saying I'm in pain. We suggest that we can use machine learning differently here. We can use it for discovery. How would we do it? Well, let's just train a connet to predict pain from the knee x-rays. So the input is image of both knees. The output is the pain score the patient gives. Notice the key distinction here. We are not predicting the KL grade. We're not predicting clinician judgment. We're predicting patient statement of pain. And notice the algorithm has access to nothing but the knee. It doesn't know anything about the patient's background or anything. It just says, I see this X-ray. That's the key. The algorithm only sees the X-rays. What do we find? What we find here is that once you predict pain, you actually get rid of basically the entire race gap. This is what you had before, and now you see the two lines just line up right on top of each other, which has a pretty stark implication. It means there was overlooked signal in knee X-rays that humans didn't know was there, which helps explain why the disadvantage of experiencing more pain. It is in their knees. In fact, it's ironic that it's what patients have been trying to tell us all along. The irony is pretty severe in the sense that here were patients talking to doctors and the doctors were not listening to them, and the algorithm could hear them more clearly than the doctor. The key to making this work, however, was that this data set on which we built it was not just we went to a health system and got some data and got some pain because A, they don't have pain, A, the sample wouldn't have been representative. This was a really good NIH study that put together thousands and thousands of such X-rays with a really nice sampling frame and a really nice data collection frame. Quality data and representative samples are super valuable. The converse of the story is very helpful too, which is why did clinical knowledge fail so badly? Well, if we went back to the original studies that produced the KL grade, for which we have clinical knowledge, and you ask, what was the race breakdown in those studies? You can't know because they didn't even have a table that told you, because they were done in Britain in the 30s and no one even thought that there was a note. It was all white people. You wouldn't have a table that said, what was the race here? There's only one race here, us. And it's a good reminder that it is not, and this echoes something Marzi said, algorithms are not the only ones prone to buggy data. People also use buggy training data. And good data can rectify human biases as well as prevent algorithmic bias. So I'll conclude on this and I'll say, I think the notion that there's buggy data here is a major problem that we need to think about systematically. It's not, as I said, not just problematic for algorithms, but for humans. But I also think there's a conceptual issue here. I don't think, at least I don't know, of really nice ways or frameworks to define a bug in this way. We have really nice ways of thinking about bugs in the programming language world. We have specifications, failure to meet specifications. We even have, automated bug detect. We have a bunch of those tools. But what is a bug? I'm waving my hands. I'm saying, is it a bug? What are those things, and how do they appear? We need some understanding of that. Moreover, I think we need tools to detect bugs. As Marzi said, we need processes, humans involved who understand everything that's happening. But as these algorithms can pick up on things that, these data sets are complex, we also need tools to be able to diagnose them. And that could be a different use of explainable AI, not to explain it to the end user for the reasons Marzi is saying is a bad idea, but instead to probe the algorithm and understand it as a partial debugging tool. Anyway, these are just an opening salvo. I'm looking forward to the conversation in the panel. Thank you.
Fantastic. That's great. And it's a really wonderful follow-up on Marzi's talk too. Sendhil, nice talk.